Okay, let's start. Good morning, everyone. Well, today we have Pau Luque. I think that most of you know him because I think that he's the person that has presented more in the seminars. So we don't have the platinum card, but we are thinking about it. So thank you very much for coming, and well, the step is yours. Thank you.
So, good morning, everyone. I'm just trying to do this every year until I get the record. Yeah, is this anybody who doesn't know me? I'm Pau Luque. I'm a PhD student of the physics program at UIB, and I work here at Medea, but I think that I know most of you, so that won't be a problem. So today I'm going to present you the last part for my PhD, which is the estimation of waves and bathymetry. This is the distribution of depth. For a sandy beach system with radar, specifically continuous wave radar. So actually, I already gave a presentation about this, which is like the proof of concept for the work I have done this last year. But today, just try to make a short introduction that in case you have want a full introduction or you're not tired of listening to me for half an hour, you can just watch the recorded video for the last presentation. So I promise I try to keep it short. A radar system is an electromagnetic and electronic system which emits electromagnetic waves, which bounce in what we call targets. This is any object in the surrounding, in our case, the sea surface. And then these reflections come back and are recorded again by the radar system. So this way, it can analyze it and get information about all the objects that reflected the electromagnetic waves, what we call the echoes of the target. So just to get a super fast review, is not use all the text, but I only want to mention that in order to do this, we need enough electronics to get a signal generated, to amplify and prepare it to be sent through an antenna, and then reciprocally an antenna to get information back, and all an electronic pipeline to process the information so it can be sampled to be analyzed in a computer. So for today's talk, I want to differentiate between pulsed radar systems and continuous wave radar systems. So pulsed radar systems are the classical ones, which just emit a high power, super short electromagnetic wave, what we call the pulse. In these orders, tens of kilovolts and below a microsecond. And then what it does, it just stops emitting and listens for all the echoes and just times the delay for each echo. And this way it can get a distribution of power received versus distance of the target. Continuous wave radars, instead, what they do is just emit continuously, that's the name, and so they cannot listen for reflections because they don't know when it arrives. So what they do is they have a time varying signal, actually they change the frequency, and so in such a way that we can compare the send signal and the receive signal to see exactly how was this delay. So in the end, we just get the same information. It is power of echoes versus distance of each reflector object. But the difference that we can emit with far lower power levels, around a watt, and also that we don't need to have this specific timing, around a millisecond. So pulsed systems are simpler, conceptually simpler electronics, but they need more restrictive components to generate this power and have this time measurement. Instead, continuous wave radars are a bit more complex in their electronics, but use not as lightweight components, let's say. So in the end, they tend to be cheaper. They are safer because you don't need these high power levels who you don't want to have near you. And so these are the ones we are going to focus on the ones we used. So also, I don't know if everybody's know this, but I will just give a short introduction about ocean wave theory for what we need. So as most waves, and now we are talking about ocean waves, not electromagnetic waves, they have two kinds of periodicities. One spatial one with repetition spacing the wavelength and a corresponding frequency, the wave number. And then if we analyze the same elevation of the sea in time, we have the period, repetition just period, and again, corresponding just frequency. So these two are not independent. This means that wave, let's say 6 seconds of period, propagating on 5 meters depth, is always having the same wavelength. But the same wave of 6 period over 2 meters depth is having a different wavelength. It's controlled by the dispersion relationship, which is actually parameterized by depth. So for its depth, all possible waves have to be within here. And this will be useful later. So what means for our sandy or nearshore systems is that a wave approaching the shore starts to have shorter wavelength, starts to be slower approaching the shore, and also have changes in its wavelength. So this means that there's a lot of spatial variability in nearshore systems. Another consequence of this dispersion relationship is that any wave train approaching the shore from any direction just tends to bend, so to be perpendicular to the shoreline. And this happens for every possible train wave. So if we have this regular wave here composed of several wave trains coming from different directions with different periods, all of them have to be over the dispersion relationship. And what we are interested in, which is the one we want to know, is just to having this list of amplitudes for each wave frequency, which is known as the amplitude spectrum. And this is useful because it allows us to characterize completely the state of the sea state in our beach, and we can have like a characteristic wave height and also a characteristic wave period. So we can use for all of our studies, and this is what we want to know. So I say this every year too, but I just want to repeat it again. Beaches, we said, are very complex systems. They have a lot of things happening. This variability we're explaining before with wave trains, but also there are currents, waves break, generate foam, just get reflected. There's a lot of sediment going by. So the message that I want to say is that it's not easy to measure here, and they change continuously. So this is why we need so much data about them and what we crave for all this wave spectrum information. So at deeper locations, it's easy because you can just place a sensor in the seabed, because you don't get the influence of the action of waves or currents, but it's not possible for our region because it just gets a lot of movement. Actually, we lost a sensor time ago, so yeah, that happens. And so a solution is just, I mean, the consequence is that it's so difficult to measure here, and it costs a lot of money, a lot of human effort. You need a lot of time to do it, and in the end, you just get measured a small zone and only few times. So an alternative is just to take the instruments out of the water and just use remote sensing. So there are different waves. You can use satellites, drones, but land-based instruments are the easiest to implement, are easier to access, to maintain, and also quite cost-effective. So video cameras are the most used, but radars are also used. So the ones we are using for this purpose are pulsed radars and in X-band. This means the frequency of the electromagnetic waves they're using, around 10 gigahertz. And so actually these systems have been used for decades now and are relatively extended. And these actually use repurposed nautical radar antennas, these ones in ships that are like this. So at this specific band of electromagnetic waves, actually interaction, the one that gets signal of the sea surface, are the small capillary waves, what we call the ripples around a centimetric wavelength. Not sure it can be seen well, but there are small, super small waves around here. And these are the ones generating the signal. And the interesting thing about these ripples is that they are generated by the local wind and traveling in its direction. So actually, to get a good measurement with a classical pulsed radar wave measurement, what we need to do, and this is an offshore measurement in an oil rig, what we need to do is just to spin the antenna continuously, identify the direction with the strongest signal, which is actually the direction of the local wind and the direction of the ripples, and just focus around here and measure the wave spectrum. So pulsed radars are the most used ones, but continuous wave radars have also been used or demonstrated that can be used to measure waves. There are actually two significant experiences in the literature, one by a Canadian research team, which just put a continuous wave radar in a wave tank, and then they put it in a boat just to measure waves in a lake just in front of them, 2 or 3 meters away. And then by an Italian team, which just measured waves, they put a continuous wave radar in the Port of Naples, and this is measured again in front of that. But the thing is that they use higher frequency systems where the interactions are different, the mechanisms are different, and also the range is shorter. So we stick with X-band radar, but with a continuous wave radar, which has not been used, as far as I know, for this end. So this is the system we used, which was actually provided by Professor Aguasca in the Polytechnical University of Catalonia. Yeah, so I want to thank him because he just prepared the whole system, modified the hardware so we can have the proper antennas, modified the software so we can have the exact acquisition scheme that we know, and he just been helping through all this study. So just to compare with the previous diagram I was showing before, here we have the power supply and all the sampling electronics, and there we have all the radio frequency electronics, this signal generation, transmitting, and receiving analysis pipeline. And these are the antennas. Actually, these are slotted waveguide antennas, which are the ones used by the nautical radars too, but these are adapted and don't have this plastic protection that we were seeing before. So this particular pair of antennas have the following footprint, which is the area they can analyze when emitting radio frequency, which is about 22 degrees in the vertical, which is enough to measure in the zone we want to measure, and about 4.5 degrees in the horizontal. We are focusing on a transect, on a small narrow transect we're measuring. But the cool thing is that in a nearshore environment, because remember before we were talking about an oil rig, here it was an offshore platform, but we are measuring the nearshore. And near the coast, what we have is that the wind tends to blow from the sea, what we call the mar, la marinada, la brisa marina, the sea breeze. And so it means that the ripples are coming in this direction. And also, as we were talking before, waves refract, so they get also normal to the shore. And this means that we can avoid having to turn our antenna around, and we can just simplify the thing and focusing just measuring in one dimension, and also doing the analysis in one dimension, which is also quite simplifying. I think it had not done before with wave radars. So what we did was to use the following acquisition scheme. We just send 100 scans, one after the other, and this happens in just 100 milliseconds. So we can have error reduction with each one of them. And we repeat this burst of scans each half a second during 10 minutes. So we can generate this time series, which is long enough and highly sampled enough to characterize this data. And this is the study site we were working with, which is Muro Beach in the Alcudia Bay, in the north of Mallorca. And actually, this is an orthophoto. This is zooming in our area. This red dot was the position of the radar. And in this location, the SOCIP is doing a biannual campaign. So they are just measuring the bathymetry twice a year. And they also keep an AWAC 3 kilometers away, which is an instrument that measures waves and currents every hour. And they are also maintaining a weather station and a video camera monitorization station in the terrace at this hotel, the Iberostar Agulla Park. So we place the radar just next to the cameras, about 27 meters above sea level and about 100 meters away from the shore. So also want to thank them because I just use all the logistics, the power supply, the internet connection. They just helped me to put this all together. And also I want to thank all the people who helped me. Diego came with me also to carry up some things up to the terrace, which was not easy. And yeah, it was fun. So the thing, we mounted the radar system and we measured during 3 different days. We have listed here. And as I was telling you, we measured perpendicular to the shore. And the system was prepared to measure up to 3 kilometers, but due to the intensity of the signal, we can only measure up to about 500 meters. And starting from this region onshore, we cannot measure because this wave breaking, so all things change. We have shoreline, so it's not used. So this is the only region we can actually measure with this radar, and should be compared this half kilometer with the around 2 kilometers that can be measured with a pulsar radar, which is high power. So as I was saying, we do all this stuff to get the signal, and this is what we get. this is what we call a time stack, a map of received power versus distance or range to the radar and time. And here you can identify some wanted events, actually people swimming, boats passing by, some birds flying, and all the funny stuff we have, passing by in a funny beach like this. And you can also identify these weird signals here, which are actually interferences, spurious signals generated by the electronics of the radar. But you can also see this repetitive pattern, which are actually waves. So if you take a time average of this information, you get this, and you can also identify the different zones. All of these are reflections, echoes produced by the land. You have the shore, you have the breaking of waves, and then you have this nice region here, which is reflections, echoes from ocean waves. And then you just have what we call the noise floor. At this point, the wave signal that goes and is reflected is so small that we cannot measure it. We just measure noise. So actually, that was telling you, and actually we're now trying to compare with the video cameras SOFIT, which were placed next to the radar, just to validate and check that all these regions we can identify here correspond from what we see on cameras. So the first thing we do is just we identify these unwanted events and we neglect them and interpolate over them. So we need to reduce this interference. Then we identify all the spurious and repeat the same thing, so we get a cleaner signal. Now, this is power received by the antennas, but antennas have a certain problem. It's not the same a signal, a wave that comes directly to the antenna, that a wave that comes from some incidence to the antenna. For example, if the wave comes behind the antenna, you don't get any signal. So we need to correct the power in different directions. But luckily, Professor Awalska had this antenna system measured, so we can correct for this pattern of the antennas. And you see we have higher powers in all the directions that are either very close or very below the pointing direction. And finally, what we need to do is this is actually corrected the received power, but as I was saying, the electromagnetic wave is just fading when it goes away, and then it has to reflect and fades away going back. But we want to get information about the reflectance of the scene. So we need to correct for this distance, and luckily we have a theoretical model for this, what we call the radar equation. So we just do a distance correction, and we get this information about the reflectivity of the wave, the ocean surface, what we call the radar cross-section. And here you can perfectly identify all these waves. Actually, you have two different ones, these more oblique ones, and these, let's say, more vertical ones, which means they're fast. And again, this is the region we can use. So this is reflectance or radar cross-section. This is intensity in the radar, but we want to get to free surface elevation. This is the changes in the elevation of the waves. And there are two ways to do it. The classical one, which is the modulation transfer function, it just assumes that the spectrum of the waves and the spectrum of the radar is related through a product with a modulation transfer function. And actually, this fancy function is just a power of the wave number. The problem with this, it corrects the shape of the spectrum, but it does not scale it properly. So you don't get any idea of the actual wave height. However, there's another approach to this, and this is a paper of 2004 by Dunker and Rosenthal. And the thing is, I don't know, it's not more widespread, but it's really nice. So what they do is they assume there's a functional relationship between this intensity, this radar cross-section, and the angle between the C normal and the radar the pointing direction to the radar. So it's like like this reflection of optics, the Lambertian reflection. So depending on how close these are, if the radar is just directing to the perpendicularly to the surface, it gets more intensity back, and it's quite different directions. It's just a feebler intensity. So what they do is quite interesting. Is they assume that the time average radar cross-section, this is the signal we get, corresponds to the average angle of the waves, which has to be horizontal. So this way, you can estimate this function, invert it, and transfer from the radar signal to this inclination of the signal. And then you can just integrate these inclinations to get the full elevation. So this is the example from this paper from 2004, and you get this relationship. And this is what we get. So now it's important to consider here some differences. They have an antenna 35 meters below, above mean sea level. They have a big range, and this means they can map a lot of inclinations, about an interval of 15 degrees. But we have such a small range, and our antenna is also not that as high. And so this means that we can only map 7 degrees of different inclinations. And that's a problem, because if we have inclinations limited, it means that when we try to integrate it, we have our waves limited. So our problem was that we're estimating so small waves. So we need to extrapolate this. The lucky thing for us is that this region is kind of pretty linear, let's say. So we try to just fit a line to it and extrapolate it to get this information for a bigger angle interval or inclination interval. But then you have to transfer from the range, it's actually, sorry, the logarithm of distance or range, and you have to transfer from this inclination. And in this is not very well posed. So this means that when you invert all these functions, you just get low, just explode. So we try different things, and in the end, instead of using the range or the logarithm of range, we end up using the observation angle, which is just this thing here, pointing direction of the radar. And so with this, luckily it's also quite linear. So we fit the line, and this time we are able to get a good transfer from the radar signal to the inclination of the sea surface. And another interesting thing is that this slope, this line here, seems to be the same for all measurements at the same measurement site. And this means that we can make a global estimation using all the measurements, and this way we get an improved estimation of this transfer line. So these measurements that were not as good or not as linear in this region, we can actually improve if we use all of them at the same time. The only thing changing is the actual level of the radar, which depends on how big the waves were that day. But was anything more signal or less signal, but this slope was the same. So once we do this, we can invert the whole radar signal into slope signal. Again, we have this wave signature. Now you can see very small region because we cannot see anything farther than this, and you can again identify these spurious ranges where we interpolated. So if we actually compute a spectrum of this, a two-dimensional spectrum, both in space and time, we get this, our spectrum to waves. And here you can identify what we were telling before, the dispersion relationship. This means all the wave energies focusing in this line, and all of this is noise. So what we can do is trying to estimate a dispersion relationship and using it to filter this spectrum. And this is quite nice because we get as a byproduct the average set of the region. So we do this, we filter the spectrum, and we collapse it to a one-dimensional spectrum. So here we have this list of amplitudes versus frequency we were talking before. Actually, it's wave power, not amplitude, but it's equivalent. And so we can identify all the waves we have. Now, there's a problem. Here we are comparing the waves we're measuring, this green line here, with the measurements from the AWAC and also from some handcuffs of TIM, the wave simulations of TIM. And so the AWAC actually was for this particular measurement, and this is quite extended, so happens for all measurements. It's showing two different wave trains. But the radar, yes, get this. Actually, it's quite small. And we don't know exactly why this happens, but actually we can try to make a global correction. This uncorrected. The green one is the one we estimated, like I explained. But if we do a correction, sorry, I lost this, but it doesn't matter. We do a correction similar to this modulation transfer function, but now with the correct scaling, we can get something similar like this. So now we are able to reproduce both wave trains. And here you have all the measurements compared. This is the actual wave height measured by the in situ instrument and measured by the radar. This is in green with the correction in black, and we have also done Teams Hankers just to get comparing, because well, we need to do it at least as good as the Hanker says, because we have more information, local information. So we actually get now with this global analysis, we get about 20 centimeters of bias and also per mean square. But if we do the correction, which we don't know if it's really extrapolable to all study sites or only to our one, we can reduce this below 10 centimeters. This is quite nice. And corrections are also quite high. So we are definitely measuring something. And this was the correction. So this is if we get all the zones, all the available zones between 200, 500 meters, and we do this compute this spectrum. But if instead of doing this, we just do different zones, use smaller zones, let's say we use actually 60 meters and overlap every 5 meters, we can also compute in parallel this pipeline for each of them. So we can get wave height distributed along distance. And we can also get depth along distance. And we don't have any comparison for the wave height because we don't have any other instrument, but we can compare with the in situ measured bathymetry from SOFIP. And you can see that we're doing not that bad in the first zone. And then what happens, you know, the dispersion relationship is quite sensitive to changes in depth for small depths. But then when you go to deeper waters, it just tends to say, no, this is deep water. So these estimations are quite error-prone. But we could identify them somehow, like saying, no, if it's more than 6 meters, you cannot trust it. But it's not that bad. And actually, this bathymetry was from March 2023, and this is from June 2024. So, I mean, it may not change that much at this depth, but who knows? And the cool thing also of doing this analysis in zones, which is something that I haven't seen done before, so, is that you can predict or you can identify somehow which zones are bad. You know, if you have this interference signal in it, then that zone is not useful, because if you do the global analysis, you need to interpolate. So you're going to have bad data. But if you do it by zones, you can just skip those points. And actually, you can identify these reasons. And well, that's all we have done. And what are we doing now? Well, as you can see, we have this bias here. We're like 20 centimeters below the actual measurement of the in situ instrument. So now Miguel is doing some simulation because, you know, the in situ instrument is 3 kilometers away, and we are measuring around half a kilometer away from the shoreline, and the wave frame can change. Waves can change during this propagation. So he's doing some propagation with X bits. And it seems that even with the uncorrected radar, we are not that bad. This is the wave height from the simulations, from the AWAC just propagated to the same point we're measuring with the radar. And in color, we have the different estimations from the radar. So it may be possible that we are not underestimating, but instead the wave just dissipated during this propagation. But these are still provisional. We're just having these results. We haven't looked at them yet. So another thing that happens is that looking at the amplitudes, what I explained, it, you have problems in low frequency because there are some modulations between wave strengths, and then you get a lot of noise in the low frequency of the spectrum. But this can be corrected if instead of measuring the amplitude of the reflection, you measure the speed of the reflecting objects. And the cool thing is that with continuous wave radar, you can also measure it. So you can repeat all the analysis with velocity. It is something we haven't done. But finally, the last thing I want to tell you is that indeed we can use continuous wave radars to measure waves. Also, that we can benefit from the geometry of a nearshore system just to simplify it to one dimension, and also that we can zonify our analysis just to get a spatial distribution over all our estimations. And that was all. Thank you all for your attention. This is just my founder. Well, is there a question? Yeah,
I have a couple of questions.
Yeah.
First one is on the when you showed the dispersion relation.
yeah.
I was wondering whether
This one?
whether you have problems when you do the Fourier transform with aliasing or
Yes,
not?
actually, this is aliasing.
Exactly, that's the
Yes.
thing.
The problem is that we cannot improve this because we cannot measure a bigger zone. Because this is aliasing cost because we don't have enough spatial resolution in this in the spectrum, and this means we don't have enough points in space. But having more points in space will mean be able to measure farther away, and we cannot because we don't have. It depends on the signal.
If you go over there, it means you need a lot higher resolution.
Yeah. I mean, we need higher resolution
You need
in
a higher
wave
resolution,
number.
more.
In wave number. So
You
this
need
means,
higher wave numbers, which means that you need to be able to measure more closely spaced things.
yes, but
not
this
far.
depends on the signal you're using. I mean,
Right,
with-
so what's
with
the
an
spatial
X-
resolution of the signal that you
this is we are sampling every half and 1.5 meters. So we are actually having
Okay.
reflectance over 1.5 meters, and this is the limit of what we can do with this wavelength. It depends on the hardware, but this just push to the limit.
I see.
But the cool thing is that since this dispersion relationship, you can parameterize it. I mean, if you have a whole spectrum, you cannot do any tricky stuff. But there's also proof in the literature that since you can estimate this dispersion relationship, you can know where this goes, so you can remap it into the LS domain. So actually, an author demonstrated that he can extend the range he was measuring just by remapping to the alias part, provided you don't have any other interference
other
signal.
funny stuff.
So you can actually go beyond Nyquist limit because you know exactly where you have to look for the aliasing, and you know that it won't be anything else. But I haven't done it yet because you have to. It's more fancy.
And the other question that I had was, in this case, you're in the, I completely appreciate that this is the correct way of going forward. You are in the most ideal case in which you can be, right? So you have the waves that come towards you in the correct direction.
Yeah.
As you move further out, I guess that
Yeah.
the waves will start to move in different directions. And how is this then mapping on or creating problems when you want to find out the angle?
Yes, that's a problem. Actually, our radar had a motor. I didn't say it, but we can actually rotate it. But the thing is that we found out that we cannot rotate it fast enough. So a solution would be just to be as like the classical system, which rotate the antenna. So instead of getting a transit, get in different directions. But we're not doing it. Actually, we want to use like this. Of course, the farther you go from the shore, the less correct is the assumption that you have normal waves. The wind, you can assume it. I mean, you can just measure in this direction or around this direction because the signal is coming from the ripples, but the wavelengths might not be as normal to the shore. So what happens then is that first, we are not mapping correctly the wave because we are not mapping the wavelength, but some projection of the wavelength. And this creates problem when we compute the spectrum. And also, we have another problem, and is that when we integrate, because we have to do this integration in the frequency domain, and this is done also by the wave number, we're using the wrong wave number. So it means that we are maybe not correctly saying where is the wave in the spectral domain, and also when we are obtaining the final result, maybe we are not having it the proper amplitude. And this may be also an answer to this problem here.
Yeah.
Why we don't have this thing and why we need a correction which is like the wave number. But this correction seems to be global for all measurements. So I think that if we have this for 3 different days, it's so difficult that the same correction can correct different directions. So I don't think this is the reason, at least for this range of distances we are measuring now, but definitely if we go further or we use a more powerful system that can go beyond this region, we should start thinking about this, definitely. Yeah.
Yeah. Can you show again the page with when you have like 100 scans every 5 seconds?
Yes.
Because I was wondering what kind of, so you say continuous wave, but what kind of wave are you sending? And also a question related to that. What kind of wave would give you the most information?
Okay. Well, actually, what we are sending, as I was saying, the wave we are emitting is continuous. We don't shut off the emitting power at any time. what we do is we sample or do not sample. So actually, when I say scans or I say burst, I mean that we just don't sample the signal that we are receiving. Okay. So the signal we are actually sending is a chip. This means this, instead of being, sorry, I have to go to the beginning. It was funny. That part was funny to me. Here. So a pulsed system uses a constant frequency electromagnetic wave, but a continuous wave system just does a frequency modulation. So what we do is actually this specific system does a triangular frequency modulation, and this means that we are sending a shorter frequency signal, then fast, then short again. And this is how we get this information about the distance, because we compare the instantaneous frequency of the sent signal with the reflected signal. And the difference in frequency gives us information about this time difference. So these ones only are useful to get us information about the amplitude of the reflectance. But, and this is another cool thing of using 100 bars, if you compare 100 not simultaneous but contiguous bars, you can also see changes in the phase of your reflected amplitude, because you compute the Fourier transform. And then it's actually like some kind of interferometry, let's say. You can actually be small changes in this echo, this reflectance from the radar. And this actually gives you the information about the speed, the velocity I was telling you before, that we want to also analyze. So this is more or less all the information I can get with this. Okay. Another question? Yeah.
On the future of works?
Yes. You made me jumping out with the slides. I should make it faster to transition.
So you said you had a problem because the AWAC is at 3 kilometers.
Yeah.
So lots of transformation can happen to the wave propagation. Yeah?
Yes.
Here you're directly comparing the simulation from Miguel are in black.
Yes.
And yours are in color. Okay.
Yeah.
Why did you try to compare directly the frequency spectrums? Because with he did with XPH.
I have the data, but I haven't covered it yet. Actually, he was providing, he just sent me this picture this last Friday or this Monday, because he just was able to get the simulation working properly, and he just sent me this graph. Is all I had until 2 days ago. And 2 days ago, when I was doing my slides, he just sent me the spectrosome. So yeah, I have to compare. Because you have so in some cases at the AWAC, you have a bimodal spectrum, as you said, so you have mixed Cs. Yes, yes. Actually, this, as Marco said, you could have different directions, average, and average from their directions. And so it would be interesting to compare with so the propagations from the AWAC position to the shore, okay, to the 5 meters. Yes. Okay. Well, actually, he goes to the shore, but 5 meters, the first one he can compare with the radar, so he has just sent me this position. But yeah, I mean, from being there, I can tell you that at least the bigger wave trend was actually normal. I mean, I was seeing it. If not, I was so sad about these measurements. But yeah, maybe the smaller wave trend may not be actually that noticeable, and might be a bit slanted towards the shore. But yeah, again, I think that if the same correction works for the different measurements in different dates, I don't think this is a problem of directions, at least at this range. I cannot be 100% sure, but yeah, I don't think this is the cause. But yeah, it would be completely interesting to compare with the spectrum, and also using the speed measurements also to see how this compares to this. Yeah. And another question: this area of Muro? Yes, sorry. Of the area of Playa de Muros? Yes. It's, let's say, from the Bay of Alcudia, it's one of the less energetic of the Bay of Alcudia, because you have shadow. Yes. The headland of the Alcudia. Yeah. Actually, the AWAC is close to one mooring zone where ships just anchor, because it's quite protected. Yeah. So what do you think? Not doing PhD because no, don't worry. But how would be your result if you would be more open ocean and coast? Yeah, I think with more energetic and maybe more organized sea. If you have swells coming from Carantana and Mistral. Yeah. Actually, for wave amplitude, I'm quite happy about this because we measured about 1 meter of wave height. So not bad at all for this, as you said, protected environment. But indeed, directions might be a problem. Why am I saying this? When we did the proof of concept of this system in the Garraf in Catalonia, instead of being a beach, it was a cliff. So actually waves were coming like this, completely slanted. So you have to point the antenna, and it starts to be tricky. So Professor Aguasca did also another test measurement in Castelldefels. And actually here you have quite energetic, but I think it's quite linear coast. It may have like more slanted wave trains, so that will be also maybe problematic. But I'm lucky because Maltese don't have any problem because this is just a demonstration that continuous wave radar can be used for this. If I have to do this operationally and for different study sites, then yes, Maltese will be used it. But that's for this, I hope.
But on the amplitude also, on the performance of the radar receiving the amplitude, you will have a big, if you have much more energetic conditions, so you will have a different weight and stiffness and all.
Yeah, well, you have a problem because you have a bigger signal, which is nice, because you can go farther, but also you have a problem which I haven't talked about, which is shadowing. You are having a radar measuring a wave, but if your wave is here and your next wave is here, this reflects and you don't have any light, any electromagnetic radiation passing by. So this means you have, after each wave crest, you have a zone where you have flags in your data. And you have to live with this. With smaller waves, this is not a problem because you have it. And also with the ranges I'm working with, this is not a problem because I'm 30 meters above sea level, so not bad. But when you are farther or when the antenna is lower, and also when the wave is of more amplitude, then you have a problem with shadowing, definitely. It's a huge problem, shadowing in these cases.
Okay. Amazing work.
Thank you.
Any other question? No?
No.
We can leave it here.
Thank
Thank you very
you.
much.